Welcome to the anti-hacking device demonstration. In this presentation, we will look at the anti-hacking device concepts in general, followed by 5 different security-related demo features and scenarios, namely secure boot, secure firmware update, the use of secure Docker containers, the integration of the hardware security module and the auto-enrollment certificate authority, and finally the use of the HSM to sign threat events. A modern car consists of many different control units interconnected with various buses, like the CAN bus. The anti-hacking device is another control unit with a specific goal to add machine learning-based security features to the vehicle. It acts as a passive intrusion detection device in the car that receives messages from other components. It is connected to the vehicle's internal buses, passively collecting and interpreting information. As a security device, it should not present an attack surface on its own. In order to secure the anti-hacking device, several security features have been implemented in order to realize a defense in-depth approach. Secure boot prevents any physical manipulations of the boot medium or the hardware. At some point, bugs or security problems needs to be fixed. To this end, a secure firmware update process has been implemented that allows frequent, but still verified updates. Still, the firmware update process is too heavyweight to adapt the device quickly to the changing threat landscape. Therefore, the actual threat detection algorithms are implemented as secure, signed Docker images. The integrated hardware security module based on the TCOS or Telecom Card Operating System technology provides a multi-purpose security anchor for use by the Dockerized applications. Finally, as a security showcase, we have implemented a threat event signing Docker image that provides threat event signing using the HSM. Secure boot is a multi-stage process with the anti-hacking device system on a chip as the root of trust. The anti-hacking device checks the signature of the bootloader against the fused bootloader key, created during production of the anti-hacking device. The bootloader in turn checks the signature of the Linux kernel. If all checks pass, the Linux system is booted successfully. Otherwise, the boot process fails. In this demonstration we see a simple attack scenario on the secure boot process. First, we insert a micro SD card with a manipulated, in our case a working, but not properly signed, boot medium. The hab_status command, HAB stands for High Assurance Boot, or Secure Boot, gives the status of the boot process as evaluated by the system. If no events are displayed, the boot medium has a valid signature. Here, the hab_status command shows lots of error events. The anti-hacking device will not boot this manipulated image. To show a good boot attempt, we insert a micro SD card with a properly signed boot medium. Again, we manually interrupt the boot process. Since no HAB events are displayed, the boot medium has a valid signature. The anti-hacking device will boot this image. For demonstration purposes, we have implemented the firmware update system as a web-based process. There are always 2 versions of the firmware installed on the anti-hacking device to make sure we have a good one able to boot. After uploading the firmware file, the firmware signature is checked before applying the firmware update. In this example, image 2 is updated. The anti-hacking device tries to boot the new firmware in image 2. There will be an automatic fallback to the original image 1 if the update turns out to be bad. Otherwise, the device will continue to use the updated image 2. In this demonstration we see how an invalid firmware update file is rejected. First, we select a bad, not properly signed, firmware image from the host computer disk. The firmware update system on the anti-hacking device detects that the uploaded file has an invalid signature and rejects it, not allowing the firmware update process to proceed. Now we select a good, properly signed, firmware image from the host computer disk. The resulting page shows that the successful upload is confirmed. The anti-hacking device now continues to update the firmware and reboots to the newly updated image. This diagram shows the development and deployment workflow for secure Docker containers. On the development PC, shown as Caramel developers in the diagram, with Docker desktop software a Docker image is created and signed. The Caramel Harbor Registry and Notary Server implement the secure registry service located in our lab in Berlin and stores the signed image. The anti-hacking device only accepts secured containers that are properly signed. In this demonstration we show the creation and upload of a signed demo image on the developer workstation. A simple Docker file is created that only outputs a Hello World message. We then issue commands to build the Docker image for ARM64 and tag it according to the name scheme for Caramel. The push command transfers the image to the registry server and signs the tag. The image can now be used by the anti-hacking device. Let's have a look at the web interface of our secure Harbor Docker registry. Content trust is enabled in the registry interface. This means that images are expected to be signed. For demo purposes, we also have an unsigned image in the registry, the SID image. See then how the newly created Hello Caramel image that we just pushed appears in the web interface of the Harbor registry. For the final part of this demonstration we log into the anti-hacking device. If we try to pull an unsigned image from the Harbor registry this fails. And we have not signed the SID image for demonstration purposes. The properly signed Hello Caramel image, however, is loaded without problems and can be run, outputting the Hello World message. This diagram shows the workflow of the initial certificate provisioning process for the hardware security module integrated into the anti-hacking device. During production the anti-hacking device is administered in the certificate authority. An initial access code is assigned to the hardware. Upon first boot, a certificate request using the initial access code for the installed HSM is used when contacting the CA. The certificate is delivered and installed to the anti-hacking device. Using the private key and certificate a new certificate can be requested anytime. This is the auto-enrollment functionality. Let's see what happens when we first start the crypto container and sample application using a Docker Compose file. The output of the crypto container in the lines beginning with TCOS1 shows the auto-enrollment process with final delivery of a certificate for the TCOS hardware security module integrated into the anti-hacking device. The new private key and certificate can now be used for applications like the threat event signing in the next demo. For this demonstration we have extended the threat event reporting workflow implemented for the Caramel project with a signing proxy that transparently signs the messages using the integrated hardware security module. Originally, threat event messages were sent unsigned as protobuf formatted messages to the backend. This opens the door for so-called slander attacks as we have named them in discussions in the 5GA misbehavior detection working group. This means the malicious sending of forged threat events in order to discredit specific vehicles or car manufacturers. With the introduction of signed threat event reporting only vehicles with correctly provisioned anti-hacking device and HSM can successfully report threats to the backend. As a new feature, we support JSON in addition to protobuf, making life easier for developers of threat detection images for the anti-hacking device. This demonstration gives a very high-level view of the sending of signed threat event messages using the proxy container. First we start the test server that emulates the backend system. Then we start the threat signing container that uses the HSM to sign threat events. We send a protobuf formatted signed message using the test driver script provided by project partner Capgemini. This also works when sending a JSON message. When looking at the test backend output and the output of threat signing container, you can see that 2 messages were verified and processed successfully. This concludes our demo session of the security features of the anti-hacking device.